Back in the day when computers were beige and engines didn't think for themselves, some clever engineers looked at a running motor and said, you know, we could probably measure how much air this thing sucks in and use that to squirt in just the right amount of fuel. And thus, the mass airflow sensor was born, the original air, sense, squirt technology. Ford adopted math way back in the late 80s, making them one of the early pioneers of mass-based airflow measurement for engine control. The old school air whisperers. So math sensors aren't new. They've been around since the 80s like hair metal and analog boost gauges. But despite their age, they're still in use today. Especially the hot wire and hot film types. They work like this. A metal wire or plate gets heated up. Incoming air cools it down. And the more air, the more cooling. Resistance changes and the ECU goes, aha, I detected airflow. To help keep that airflow smooth, there's a screen that helps take out vortexes and turbulence. Now, unlike older flat door vane meters or weird Kármán vortex setups, hot wire maths don't need an external air temp sensor. Hot wire and hot film sensors can be coupled with a dedicated air temperature sensor, but they don't require one. We saw earlier that the metal is heated by an electric current to measure air mass. And here's where the science kicks in. Electrical resistance goes up as the wire gets hotter. So when the air rushes past, it cools the wire, the resistance drops, and the sensor needs less voltage to keep that wire at the target temp. With this change in voltage, math can calculate how much air is moving over the wire based on how much the electrical current changes. Now, the vane airflow meter is phased out, but it used a flapper-style meter where air intake hits a measuring plate, and the movement of the plate produces a voltage signal proportional to the air intake. And the Kármán vortex AFM, it creates and counts vortexes in order to measure airflow. You can see the meters kind of rely on producing an electrical signal that can be measured. Now, the raw voltage signal is useless unless you know what to do with it, right? That's where math transfer function comes in. There's basically a lookup table or curve that converts that sensor voltage into grams per second, or some other secret sauce, depending on the ECU. For hot wire maths, that curve usually looks exponential. Why? Because of physics and the size of the pipe it's living in. The shape of the curve is usually determined by the physical characteristics of the sensor. The metering range of the sensor is usually determined by the cross-sectional area of the housing it's in. So here's a party trick for you. Want to make your math handle more air? Put in a bigger pipe. Yep, same sensor, different diameter, different airflow range. All you have to do is rescale the math transfer function using the cross-sectional area. Seriously. Double the pipe diameter and the cross-sectional area quadruples, meaning the same sensor can now meter 4 times the air, with a simple math adjustment to the curve. Quick quiz time. Don't worry, it's not hard. A 2-inch pipe reads up to 1,000 grams per second. What happens if we put in a 4-inch pipe? A 4-inch pipe equals 4 times the area. Area goes from pi 1 squared to pi 2 squared. And so from pi to 4 pi, and you're getting 4. Now it can read up to 4,000 grams per second. Just multiply each point in the math table by 4. Boom. Boom for gains. A lot of times math tubes are used, and they essentially change the sensing area of that cross-section without changing the overall pipe diameter. Also, you can technically use a calibrated version of the math sensor if you can't recalibrate your ECU tables. A calibrated meter has the exact same flow characteristics as the stock meter, but at higher air mass. A typical use would be when converting from stock to aftermarket fuel injectors, and these calibrator types are designed for use in a specific application. So if you toss this meter on a car with those injectors and a stock calibration, it'll run okay, sort of. Here's the beauty of math systems. Fueling is pretty simple. Math sensor gives airflow, ECU multiplies by target AFR or lambda, times injector size, adds injector latency, and done. Injectors fire. The math knows airflow, and the ECU knows how much fuel is needed for that amount of air. Timing, same idea. Use the mass sensor to get the airflow, combine with RPM to get grams per revolution, and feed that into your spark table. Most ECUs just stop there, but gram revolution is your spark axis. But Ford said, let's get fancy. They use load with a capital L. L is airflow per revolution divided by the engine displacement. So it's basically real-time volumetric efficiency. Same idea, different flavor. And yes, math-based spark maps look very different from speed density ones. So if you're switching over, be careful. Timing that worked under SD could knock like a woodpecker in a drum line with math. Math systems usually use load and RPM to figure out what AFR or lambda to shoot for. You're cruising, it's going leaner. If you hammer down, rich. Idling at a meet while arguing about ethanol content, somewhere in between. Some setups use TPS instead of load, but the goal is the same. Pick the right fuel mix for what the engine's doing. Let's be real, math isn't cutting edge anymore. But it's still around for some pretty good reasons. Extremely accurate for fueling in steady state, like cruising on a highway at constant speed. It autocorrects for altitude, weather, and some minor mods. No need to retune if you swap intakes, headers, or cams, as long as the airflow path stays clean. And that's kind of a big thing. But math has its quirks. So math systems aren't perfect. There's vacuum leaks and you may run lean due to unmetered air. Twisting the sensor changes the reading. Bends or bumps near the sensor. Turbulence ruins the accuracy. We have math housing is too small. That can choke the power. Dirty wire could give you bad reads. Cam overlap. Reversion makes the sensor count air twice. And throttle slam, math reads it after it happens. So math also has relatively poor response to transient conditions like sudden throttle changes. So it might be legacy tech, but it still does the job. It sucks in air, it senses how much you've got, and it tells the injectors when to squirt. It's not flashy, it's not new, but it's dependable, it's tunable, and still used in modern cars every day. And that's why air-sense squirt isn't just a joke, it's the heart of math. Keep the air flowing, and we'll see you next time.